Hello everyone, welcome to my channel. In this lecture, we will discuss about the adsorption isotherm. So, adsorption isotherm, adsorption isotherms. What are isotherms? So, these are the constant temperature curves. For example, this is a curve which is obtained at some temperature, suppose at 15 degrees centigrade. So, this constant temperature curve is called the isotherm. On the x-axis, it can be partial pressure, it can be concentration, equilibrium concentration, and on the y-axis, it can be equilibrium uptake. So there are various types of isotherm like Langmuir adsorption isotherm, Freundlich adsorption isotherm, Temkin adsorption isotherm, Langmuir-Freundlich adsorption isotherms. There are various types of adsorption isotherms. So usually these isotherms are obtained from the equilibrium study, from the adsorption equilibrium. So, for example, in adsorption equilibrium, suppose we have the information about equilibrium concentration and equilibrium uptake. There are some values of equilibrium concentration. Suppose equilibrium concentration is suppose it is 200, and here the equilibrium uptake is suppose 30. Here the equilibrium concentration is suppose to 10, and the equilibrium uptake is 35. Here again, for example, equilibrium uptake is concentration is 220 and the uptake is this one. So from these points, suppose on the x-axis we plot the equilibrium uptake, concentration, and on the y-axis we obtain the equilibrium uptake. So suppose this is one point, there is another point, and there is another point. So when we combine these points, we will get isotherm. And suppose this whole experiment is taking place at 15 degrees centigrade. So this curve is obtained at 15 degrees centigrade, and this curve is called the adsorption isotherm. This equilibrium uptake is nothing but it is the milligram or mole per gram catalyst, or it can be the milligram per gram catalyst. So how much adsorbate are attached to 1 gram adsorbent? It is nothing but it is shows that how much adsorbate are attached to 1 gram adsorbent. It is called the adsorbent uptake. So uptake is nothing. Adsorbent uptake or the catalyst uptake is nothing but it is shows that how much mole of adsorbate attached to 1 gram catalyst, or how many milligram of adsorbate are attached to 1 gram catalyst. So these are the uptake, equilibrium uptake, and this is the equilibrium concentration. Its unit can be ppm, parts per million. Its unit can be milligram per gram per liter, which is again ppm. So its unit can be it can be, this can be per gaseous space. It can be the partial pressure of component A, and this can be the equilibrium uptake. So uh, these are the adsorption isotherm. Suppose at 10 degrees centigrade we obtain this isotherm, at 20 degree we obtain this, at 25 degree we again obtain this isotherm, at this isotherm. So there are various these are the isotherms. So isotherms also show us that whether the adsorption process is feasible or not. Whether the adsorption process is feasible or not. From isotherms, we can determine that which isotherms from adsorption equilibrium, actually from the adsorption equilibrium, we can determine that which type of isotherm is best fitted to our experimental data. So, which type of isotherm are best fitted to our equilibrium study, to our adsorption equilibrium study. So there are various type of isotherms. Like for example, this is Freundlich adsorption isotherms. This is the mathematical form of the Freundlich adsorption isotherm. This is the equilibrium uptake of the adsorbent. This is the equilibrium concentration of the adsorbate, and this is the Freundlich constant. And this n is the intensity coefficient or the intensity factor of the adsorbate. and this also shows the interaction between adsorbate and adsorbent. So this is the equilibrium concentration of component A. Component A can be lead ion, it can be the chromium ion. In the aqueous phase, it can be the equilibrium partial pressure of carbon monoxide. So these are the equilibrium concentration or the equilibrium partial pressure of molecule or ions. This is the equilibrium uptake. Again, its unit can be milligram per gram for liquid case, for ions, and for gaseous case, it can be mole of gas per gram catalyst or per gram adsorbent. So this is the Freundlich constant. It can be also written as Kf, and this is the intensity factor. It shows the interaction between the adsorbate and adsorbent. Suppose this is the adsorbent and this is the adsorbate. So how the adsorbate are attached to the adsorbent? How, whether the interaction is good or not? So it can be determined from this n factor, this n number. This is a number, a constant number. So suppose now, suppose we have done some experiment in lab, and the experiment is related to the adsorption of carbon monoxide molecule on the catalyst surface. So suppose the partial pressure of carbon monoxide in kilopascal. This column shows the carbon monoxide partial pressure in kilopascal, and this column shows the adsorbent or the catalyst uptake in mole of the carbon monoxide molecule which are adsorbed on 1 gram catalyst particle. So this is catalyst particle and this is the carbon monoxide molecule which are attached to the adsorbent or catalyst. So this is the gram or mole per gram catalyst. And the partial pressure of carbon monoxide in the system is, suppose this is a system. So the partial pressure of carbon monoxide is Pc, partial pressure of carbon monoxide. So, for example, if the partial pressure of carbon monoxide is 1 kilopascal, the adsorbent or the catalyst uptake is 1 mole per gram catalyst. When partial pressure is 2 kilopascal, the catalyst uptake will be 2 mole per gram catalyst. When the partial pressure of carbon monoxide is 3 kilopascal, then the catalyst uptake will be 3 mole per gram catalyst. And when partial pressure is 4, the uptake is 4. When this is 5, this is 5. When this is 6, this is 6. When 7, it is 7.1 suppose. When 8, it is 8.29. So these are the experimental data. Here you can see when the partial pressure of carbon monoxide is 14 kilopascal, that is 8.2. The adsorbent or catalyst uptake is 8.2. So from 9, after 9 kilopascal, you can see after 7 kilopascal, here you can see the adsorbent uptake is become constant. So this is the equilibrium uptake. This is the equilibrium uptake, which is QE, the equilibrium uptake of the catalyst, because these are constant value. And here the partial pressure changes, but the uptake is constant. So here you can see this is the partial pressure of carbon monoxide, and here this is the uptake. Suppose this is the adsorbent uptake. So first it is increases, then after a certain time it become constant. So this constant region shows the equilibrium uptake here, 8.2 for these runs. And these are the partial pressure. Suppose this is 1 kilopascal, 2, 3, 4, and here this is 7 kilopascal. Suppose after 7 kilopascal, the equilibrium uptake is become constant. The adsorbent uptake become constant. So graphically, we can represent the experiment in this form. Suppose when partial pressure of carbon monoxide is 1 kilopascal, the catalyst uptake in mole per gram is this is the uptake of catalyst. It can also be written as, okay. So here you can see at 1 kilopascal, you can see the catalyst uptake is 1. At 2 kilopascal, the catalyst uptake is 2. Suppose at 3 kilopascal, catalyst uptake is 3. At 4, it become 4 here. After this point, you can see after 6, after this point, suppose you can see this, suppose this point. After 8, you can see that the uptake become constant. It become constant. So this is the equilibrium uptake. Equilibrium uptake of catalyst. And these are the, after this point, these are the equilibrium partial pressure of carbon monoxide. So 9, 10, 11, 12, 13, 14, these are the equilibrium uptake. So these are, suppose these are general case. Uh, so this is a graph which we obtained from our experiment. So experimental graph. These are suppose our experimental graph. Now we will check that whether this graph is related to our experimental to our model or not. So we will made a model, and then after making a model, we will compare our model or adsorption as we will compare our model with this experimental graph. So first of all, we will make a model, adsorption model, and after model making model, we will compare our model with this experimental graph, that whether our model is related to this graph or not. So uh, okay, the example was related to the adsorption of carbon monoxide on catalyst. So let's whether our experimental data fit with our proposed isotherm. So we will suppose, first of all, we will propose isotherm. So suppose this graph is related to the Langmuir isotherm. Suppose this data is fitted to the Langmuir isotherm. So suppose this graph is similar to the Langmuir graph, Langmuir isotherm. So suppose this Langmuir isotherm, we assume that this is Langmuir isotherm, Langmuir isotherm, which is obtained at some temperature like room temperature 20 degrees centigrade, suppose. So this is isotherm. This is isotherm. This graph is isotherm. And suppose this is Langmuir isotherm. Now we will make Langmuir isotherm. We will make a model of Langmuir isotherm, and after making a model, we will compare our model with this experimental data, with this graph, whether it is okay, whether it is matching with our experimental data, or whether our model is matching with our experimental data or not. If our experimental data is matching with the Langmuir isotherm, then our data will fall on this isotherm. If it is not matching, then our data will the data will be very there will be no correlation with our experimental and graphs. So the regression coefficient will be very small. Okay. Now suppose let's whether our experimental data fit with our proposed isotherm, Langmuir isotherm. We propose Langmuir isotherm. So we make isotherm about the adsorption of carbon monoxide. So this is a carbon monoxide molecule. It is, and this is the active side. This is the catalyst side. So this is a catalyst. This is catalyst. This is the active side of catalyst. The carbon monoxide molecule is adsorbing on this side. So this is the adsorbed carbon monoxide molecule on the active side. And this is the vacant side. There is no molecule on this side of catalyst. Okay, so the adsorption of carbon monoxide on the active side is carbon monoxide is attaching to the active side, and this is the adsorption rate constant Ka. So the rate of attachment of carbon monoxide on the active side is equal to minus RCO. The rate of attachment of carbon monoxide is denoted by minus RCO. So the rate of attachment of carbon monoxide. Because carbon monoxide is decreasing in the gaseous phase, so this negative sign is, there is a negative sign, and it is equal to the rate constant, the adsorption rate constant, multiplied by the partial pressure of carbon monoxide in the gaseous phase and the concentration of the concentration of vacant side, this vacant side, this vacant side. So here, this is K adsorption rate constant, the partial pressure of carbon monoxide. Carbon monoxide is a gas, so for gas we will use the partial pressure. For liquid we will use the concentration. So the concentration of active side is this one, Cv. So this is minus RCO is equal to KAPCO and to CV. Concentration of vacant side is denoted by CV. So this is equation number 1. Okay. Now this is the rate of attachment of carbon monoxide on the active side. So this is the adsorption. Here this arrow shows us the adsorption of carbon monoxide, and this arrow shows the desorption of carbon monoxide from the active side. So the rate of desorption. So first in equation number 1 we have obtained the rate of adsorption. Now we will discuss about the rate of desorption of carbon monoxide from this active side. From this active side, this is adsorbed and now it is desorbing from active side. So active side will, this will be desorb the carbon monoxide and this will be the active side. So the rate of desorption, it will be, the desorption rate constant will be denoted by K minus A. So the rate of detachment of carbon monoxide from the surface. So the rate of detachment or the rate of desorption of carbon monoxide from the active side is equal to minus RCO into S. It means that the rate of desorption of carbon monoxide from the active side is equal to the desorption rate constant multiplied by the concentration of carbon monoxide at the active side. So the concentration of carbon monoxide at the active site will be denoted by C, concentration of carbon monoxide at the active site. So this one. So the rate of attachment. Now the rate, this is the rate of detachment. So here negative sign. So the rate of attachment will equal to this negative sign will go to this side and it will become the rate of attachment of carbon monoxide on the active side. So the rate of attachment of carbon monoxide on the active side will be equal to RCOS is equal to minus this negative sign will go to this side. This will become positive. So it will be equal to this positive minus K minus A into CCO into S. This is equation number 2. Now combine equation number 1 and 2. We will get the net rate of attachment of carbon monoxide on the active side. So the net rate of attachment of carbon monoxide, the net rate of adsorption or the net rate of attachment of carbon monoxide on the active side will be equal to the adsorption rate constant into the partial pressure of carbon monoxide into the concentration of vacant side minus the rate of detachment, the detachment rate constant or the desorption rate constant into the concentration of carbon monoxide at the active side. So again, this Ka, the net rate of adsorption will be equal to minus is equal to Ka. This will come out and it will be equal to partial pressure of carbon monoxide Cv minus the concentration of carbon monoxide at the active side divided by Ka divided by the rate of attachment divided by rate of detachment. Now this rate of attachment divided by rate of detachment is nothing but it is the adsorption equilibrium constant. Adsorption equilibrium constant. It is denoted by capital Ka. So the adsorption equilibrium constant. The K is the adsorption equilibrium constant. So in place of this Ka divided by K minus A, we will write the capital Ka, which is written in this equation. Adsorption equilibrium constant. So the net rate of adsorption of carbon monoxide on the active side is this one. Now, now the net rate of adsorption of carbon monoxide at the active side is equal to Ka into PCO Cv minus CCO and to S divided by adsorption equilibrium constant. This is the net rate of adsorption of carbon monoxide on the active side. So at equilibrium, the net rate of adsorption of carbon monoxide on the active side will be equal to 0 because at equilibrium, the rate of adsorption will be equal to the rate of desorption or the net rate of adsorption is equal to 0. So when the net rate of adsorption is 0, this this will be equal to 0, and when this equal to 0, this term will go to this side. Divide anything divided by 0 will be equal to 0, and when we rearrange this PCO and to CV, this K will multiply with this, and it will be equal to the concentration of carbon monoxide at the active site. This is equation number 4. Now we will write the site balance. So the site balance is nothing but it shows us the number of sites. So the total number of sites is equal to vacant site plus the site on which the atom are adsorbed. So the site on which the carbon monoxide are adsorbed. So the site balance is this one. So here you can see the total site is equal to the site at which carbon monoxide is adsorbed, this one, and the vacant site. So the total site is CV plus this one. It will give us the total site. This will give us the total site. So from here you can see Ct minus CCO and to S will equal to C. So rearrange this will go to this side, it will become negative and it will be equal to vacant site, concentration of vacant site. Okay. So now in place of CV, we will write this term. Because CV is equal to Ct minus CCO into S. We will put the CV value is this one, so this put this value in this equation in place of CV. We will get this equation. Now rearrange this equation. We will get that CCO S plus N to 1 plus PCO into Ka is equal to PCO Ka into Ct. Now further rearranged. So the adsorption of carbon monoxide, this is the adsorption of carbon monoxide at the active site is equal to the partial pressure of carbon monoxide in the gaseous phase multiplied by the adsorption equilibrium constant multiplied by the total number of sites divided by 1 plus the partial pressure of carbon monoxide, which is equal to this one, and to the adsorption equilibrium constant. So now equation number 5 is nothing but it is the Langmuir isotherm. And generally the Langmuir isotherm is nothing but it is like this one, 1 plus the Langmuir constant and the partial pressure of a gas. For gaseous system it will be the partial pressure, for liquid it will be the concentration. So I'm talking about the gaseous phase, so it will be the partial pressure of gas A suppose, and the partial Langmuir constant, partial pressure of gas A, and to some constant it will be equal to the equilibrium uptake. It will be equal to the uptake. Suppose this is Q is uptake. Now this Q is nothing but it is the carbon monoxide uptake. This is the uptake of the catalyst. So now the uptake of the catalyst side, the carbon monoxide uptake is equal to this one. This is the Langmuir isotherm. Now case number 1, at low partial pressure, when the partial pressure of carbon monoxide is very small, so this term will be equal to 0. That will be neglect. We will neglect this term. So the carbon monoxide uptake will be equal to the partial pressure of carbon monoxide, Ka equilibrium, adsorption equilibrium constant, and to the total active site. So this one, Ct. Now this Ka and Ct, these are constants. So combine these two constants, we will get another constant which is K prime. And this is the partial pressure of carbon monoxide. And this is equal to the carbon monoxide, the catalyst uptake. The carbon monoxide uptake of the catalyst. So the carbon monoxide uptake will be equal to this K prime into Pc naught. So here you can see that the catalyst uptake is a linear function of the partial pressure of carbon monoxide. So here you can see that the catalyst, this is the catalyst uptake, and catalyst is adsorbing the carbon monoxide molecule. So carbon monoxide molecule are adsorbing on the catalyst, and the catalyst uptake is this one. And it is a linear function because you can see it is a linear relation. This is some constant, and here you can see the partial pressure of carbon monoxide. So when the partial pressure of carbon monoxide increases, the catalyst uptake will also increase. In this case, in case number 1, at low partial pressure of carbon monoxide. So, okay, now you can see here from the graph, this one. Here you can see I am using some other color like this one. Now here you can see this is low pressure region. Here you can see up to 8. When the partial pressure of carbon monoxide increases, the catalyst uptake also increases, and it shows linear relation up to this point, from 0 to this point. It shows linear relation here. So at low pressure, partial pressure is a linear function of the catalyst uptake. Now I am going to higher pressure. This is case number 1. Case 1 for Langmuir isotherm. Now I am using the higher pressure, and case number 2. Okay, I'm using the case number 2. So now at higher partial pressure of carbon monoxide, for example, when partial pressure is greater than 8 or 7 kilopascal, suppose, then the this is very high. We cannot neglect this term, so we will neglect 1 of the denominator. Now, when we neglect this term, then we will cancel this one, this one, this one, and this one. So here the adsorbent or the catalyst uptake will be equal to Ct. The catalyst uptake will be equal to Ct, which is again some constant. So at higher pressure, the catalyst uptake will be constant. Suppose this was the first case, it was linear. Now at higher pressure, the catalyst uptake is constant. This is constant. This is case number 2. This was case number 1, and this is case number 2. So here at higher pressure, this is at higher pressure, 8 or 9 kilopascal, the catalyst uptake is constant. This is the catalyst uptake on the y-axis. So adsorption of carbon monoxide on the catalyst follow the Langmuir adsorption isotherm, and it is shown from the experimental graph. So go to the experimental graph and now check it, that at 8 and 9 kilopascal. So here at 8, 9, 10 kilopascal, the adsorbent uptake or the catalyst uptake is constant. Here you can see uptake is constant. This yellow one. The catalyst uptake is constant. This is constant. 8 mole per gram. So here the catalyst uptake is constant. So from this experiment we conclude that our experimental data is best fitted to the Langmuir isotherm. So the adsorption of carbon monoxide on the catalyst follow Langmuir adsorption isotherm. So we can, okay. So sometimes we need a linear. Now sometimes we need the linear form of isotherm to get constant of isotherm. Sometimes we need the constant of isotherm like the Langmuir constant or the some other constant, so or the adsorption equilibrium constant. So we need linear form of adsorption isotherm. So we need the linear form of isotherm. So this is the not the linear form. This is the non-linear form of isotherm. To get the linear form, so we will rearrange this equation. So this term will go to this side, and this term will go to this side. It will be look like this one. Now the partial pressure divided by the adsorbent uptake, so it will go to one side, and this term will go to this side, so we will get this equation. And now this is 1 divided by KACT plus PC naught KACT will be equal to partial pressure of carbon monoxide in the gaseous phase and the catalyst uptake. So here you can clearly see that this is the y-axis. This is y. This will go to the y, and this is, you can see, this is the y-intercept, which is c. Y is equal to mx plus c. So this is the y-axis. This is the x-axis. This is the y-intercept, and this is the slope of the linear line. So suppose this is the x-axis, this is y-axis, this is y-intercept, and this is slope. This is m, This is the y-intercept C, and this is the slope. M is the slope. So here you can see on the y-axis partial pressure divided by adsorbent uptake or the catalyst uptake is equal to 1 divided by Cut and partial pressure divided by Ct. So here you can see this C is nothing but this is the y-intercept, and this is the Pc is the partial pressure of the carbon monoxide in the gaseous phase is on the x-axis. So this is the x-axis. This is the x, the partial pressure of carbon monoxide, and 1 divided by Ct. 1 divided by Ct is the slope of this line. So 1 divided by C is the slope of the line. So again, clearly you can see here, if slope is given, suppose if slope is 2, so here we can obtain the active site concentration. So it will be equal to 1 divided by 2. It will be 0.5. Active site concentration will be 0.5. So from slope we can get the active site, and from y-intercept, suppose if y-intercept is 1, so here you can see C is equal to 1 divided by Ka into Ct. This is the linear form of this equation. The linear form of this equation is this one, this equation, and this equation is written in graphical form, which is this one. This is the slope. Slope is 1 divided by Ct. This is the y-axis. This is the y-intercept. So suppose if the y-intercept is 1, so we will get Ka Ct. Now we have already obtained Ct 0.5, so put Ct 0.5 in this place. We will get the Ka value, the adsorption equilibrium constant value. So we will get the adsorption equilibrium constant value, which is it will be equal to 2. And now this is the x-axis. This can be obtained from experiment. So the partial pressure, this is the x-axis. So this is the x-axis. Here you can see the x-axis the partial pressure in this experiment, and the slope is this one. Here you can see this is the slope of the line, and this is the y-axis. You can see this is this Pc is partial pressure of carbon monoxide divided by catalyst uptake is on the y-axis, and this is the y-intercept. So the y-intercept, here you can see the y-intercept. So from this we can get the Ct, the total concentration of active sites. We can also obtain the adsorption equilibrium constant. So this was all about the adsorption isotherm. Thank you very much for your attention. If you are new to the channel, please like and subscribe. In the coming lecture, we will discuss about the surface reactions. Thank you very much.